Okay. So yeah, again, thank you so much for agreeing to present. Looking forward to the talk. If there are any questions, you guys can write it in the Q&A. Actually, there's a Q&A, and we can like then voice it out. And we will upload the recording to YouTube. So if you want to rewatch it, there it is. Okay, all yours.
Okay, cool. Thank you. All right, everyone. Hi, I'm Mun Hong, and I'm currently a first-year PhD student at Duke University. So I am based. So this is a work that I previously done at the Coley group at MIT, and namely this is called Flower, which is mainly doing flow matching for electron redistribution. Mainly, we're trying to tackle the problem of reaction prediction. So an outline of what I'll be covering today. We'll go over some of the motivation and the background of building Flower. And then we'll talk a little on representation and modeling. Um, and then maybe some about the architecture and also discuss the results that we got from Flower. Cool. So let's start with the motivation and background. So I think we started off this project motivating the idea with the motivation that we want to conserve the law of mass conservation. So this was actually demonstrated by Antoine Lavoisier in like 1789, where mass cannot be created nor destroyed. So this is actually prevalent in the idea for chemistry and also fluid dynamics, where we cannot create mass from vacuum, and at the same time we don't see mass destroyed into vacuum. So the entire mass of conservation holds within this principle. So when we when we zoom into these chemical reactions, we then see that these laws are actually obeyed, and we would normally describe chemical reactions as in terms of transferring of electrons. So this was actually first postulated by Sir Robert Robinson, where these curly arrows represents how the electrons move. So that we can build bonds or break bonds, going from reactants to products. So as we move towards the machine learning models that are trying to tackle such problems, we see a lot of models that are tackling this problem in terms of end-to-end prediction. And what do I mean by that? So we started off with some pool of reactants, and then there's this target ground truth that you're trying to train against, and then you're doing exactly the end-to-end prediction that moves you from the reactants to the product. So this is like some of the prominent works are like seek-to-seek, WLDN, some transformers, some graph-based models. All these models, they mainly train on just the reactants and then just the major product. And so we can see that the arrow pushing diagram or the arrow pushing formalism is not actually present in such kind of models. And this is actually mainly due to there are not really any intermediates that are present in the database, and also like byproducts that will be imputed from some of the elementary steps that we could do. Plus, there's actually limited data for mechanism prediction. So the key question that we're trying to answer from this model or this direction is actually building models that better aligns with chemist intuition. So so this is where we started off. So we know that we have a data set issue. So we started off with a paper where we actually manually hard coded a lot of the textbook examples. So different types of reaction which constitutes different types of elementary steps. We would then say, given a USPTO data set, we would impute the elementary steps onto the reactants so that we will be able to get those intermediate steps. So as you can see, it's like this is the conventional global models, and then what we do is basically just trying to say, apply this elementary step, apply these elementary steps, and then it just moves us towards the final product. So this was a very, very long and tedious work done by Jun Young himself. he was a postdoc back then, and I think those elementary steps, from textbook, from the internet, he slowly impute them, and that actually helps us to generate the entire smarts data set for different types of reaction. So with that,
I have a question. Sorry.
Yeah, go ahead.
Yeah, regarding this data set. So like you mean it's elementary steps and you don't have this full pipeline. It's just you're trying to build a data set where you have one phase one, like I don't know, 2 molecules, and then you need to predict what will happen at the next step, or like how exactly is?
I'm not really hearing clearly. If you are able to get closer to the mic, it will be better.
Yeah, sorry, do you hear me better?
Yeah, I can hear you better.
Yeah. My question was like, so you said that this data set was built with, I guess, chemist intuition and like elementary steps of how like things would break or bond. Is it like you have, I don't know, one step and then the next step based on this elementary step, you show these in the data set, or what exactly are the...
So basically, for these elementary steps, they are normally encoded in smarts, right? So what is like, they will enumerate. So let's say if a CC bond is breaking, they will track all of the possible CC bond and then like break them. Or like let's say if there's a specific substructure that they're trying to match, and then they'll match it and then they'll break it. So like you can think of it as there will be like a very large tree of like stuff that goes on, because like you just constantly put the new elementary step and then like it propagates and propagates. So there's some sort of pruning that is done that I'm not really covering today, but that's for another previous paper that we did. Yeah.
Right, very clear. Thanks.
No. Cool. So in that previous paper, we actually also did we actually also trained models on it, where we used mainly models from our lab, the WLDN, the graph the transformer models, and also graph to smiles. And we see that in some way they are actually learning quite well. These elementary steps actually correspond well to they are able to recover based on what they learned in the training set. And we thought that this problem might be somewhat solved if we have such kind of data set. But apparently, as we look deeper into the models, we know that at least for the WLDN, which is actually a graph model that combinatorially enumerates all possible bonds, this actually suffers the combinatorial explosion problem. And as for these transform models that are actually the dominant players right now, they actually suffer when it's actually predicting autoregressively. It's actually generating atoms or like deleting atoms, which causes alchemy, and it's actually not the intended thing that we wanted to do. As we motivate the entire problem that we wanted to do. We want to conserve mass throughout the entire reaction prediction. So with that in mind, we actually, as we were trying to solve this problem, there were a couple works out there by Pierre Baldi, where actually he covered how he in one of the ML models that he built, he had a part where you would first identify the reactive sites of the like, let's say, identify all the possible reactive sites, the orbitals that are going to be involved in the reaction, and then afterwards then rank the possibility. So we would be able to see then this type of conservation, because right now he does also have his own mechanistic data set, and with this type of training in the level of abstraction of elementary step, you're able to then conserve the mass throughout the entire reaction prediction. But in this case, we found out that at least for us, we do not really like the formulation, because there's these two steps where you want to identify the reactive sites, and then you want to rank those reactive sites. And this type of models which are trained separately, there are potentially problems of error propagation. So we decided, we sort of thought that there could be a better formulation to actually think about such kind of problems. So to go back to the motivation to after going through all the possible limitations, the main idea that we're trying to go for is we want to conserve everything, going from heavy atoms to hydrogens to electrons, and then we're trying to avoid alchemy at all costs. So, and at the same time, we would like to also predict electron movements all at once. So we would not just want to predict just one step, just as like the mechanism prediction. We want to actually predict all of these steps simultaneously. So going from one elementary step to the other elementary step, we do not want to be like ranking, oh, this is first, this is second, or like, because in the actual real world, or in the actual simulation of electron flow, we don't like electrons does not move in this manner, where like in a sequential manner. So we would want something that is one shot, or like they predict end to end in this case. So we see that in terms of the translation formulation, it's able to satisfy the end-to-end prediction, where you just one shot create the entire product, but it fails to do mass conservation. For the sourcing formulation, which is the previous period of this work, we are able to in some way conserve mass, right? But end-to-end prediction means that having two models. So we wanted to have something that is able to do end-to-end prediction and at the same time mass conservation. So when we look deeper into the representation from Peabody, we see that there's this constant loop of predicting the sourcing and then rank the possibility, and then just moving back and forth until it predicts the entire reaction pathway. So what we were actually what we kind of sort of think that was possible that is a solution is where right now we think of all of the possible atoms and bonds will be in the outgoing edges. This is where everything will start donating, and then incoming is where all of these will potentially be receiving electrons, right? So or forming bonds in this case. So this type of like matrix where someone donates and then someone accepts sort of captures the intuition of like, oh, it might be that, let's say if we just predict this matrix, it would probably just work. So when we think about, oh, maybe this might be a good representation, but after sort of like the deeper discussion and trying to identify potential problems, we found out that there's actually cases where, let's say, if the outgoing edges start over donating electrons from the outgoing edges, and then the incoming edges will then be receiving too much electrons. So in some way we could say, oh, let's just fix it using the octet rule assumption, right? You just constrain how much electrons you can donate. But this does not really generalize to the f orbital, where there's 12, there's 18 electrons, and then there's like and it's not really known how they actually form bonds, because sulfur can form 8 bonds. So that's why it becomes like kind of iffy. Like we can't really work in this manner. So, and then it actually gets really large. Let's say if you have 200 atoms, and then the bonds will be like twice as much. So it will be actually a really, really large matrix. So this matrix wasn't like that intuitive as or like that well formulated. So that's why we decided to not move on. We decided to kind of move on with this representation. So I think.
Sorry. Before you go on, I have a quick question regarding the first disadvantage. Like, can you explain again what was the reason why you had over donation with that matrix representation?
Okay. So for example, let's say you have 8 electrons that let's say you have 8 electrons. So if you okay, so for example, each row, like you would say you can only donate, let's say if you're a chlorine, you would normally form one bond, but in fact chlorine is of is it d orbital. So that's where like you can potentially form or let's say iodine, right? You can potentially form more bonds than one. So you can't really constrain, say, just you can only donate one. You can actually donate more than one. So it becomes, you can't really say which one helps you to force or conserve the mass in this case. Like you can tell how many you can only donate, if that makes sense. That
Yeah, makes sense.
Okay. Okay. Cool. All right. So so when we start, falling back into going back to the drawing board, I think the original idea of matrix still actually holds, that we want the matrix representation, but we needed something different in the entries. So looking at adjacency matrix, when we, let's say, draw a molecule, we would say form this bond, form that bond, so it would be 1 0 1 0 1 0, right? And if it's a double bond, it's 2. So that actually leads us to, like, what if it's electrons, right? Let's say single bond, like 2 electrons, double bonds like 4 electrons, what triple bonds like 6 electrons. So let's say if we fill the entries, would that be a better representation? So that actually leads us to actually the bond electron matrix formulation, where all of these entries right now will be the electrons. And then basically let's say for a change of electrons would mean a delta B matrix here. So this change would be applied onto the entries. So you're basically shifting the electrons. And then that means, let's say, going from the starting reactants to the product would, let's say if you just apply delta B matrix, that moves you from the reactants to the product. So this, to start kind of illustrate what's going on, like this might be a very easy way to look at it. So imagine all of the bonds, imagine all of the atoms, you break, and then you move all of the atoms to the rows axis. So one thing also that is very elegant about this approach is that now you don't really have to represent all the bonds, because bonds can also break and then the electrons can flow to the atoms, right? Right now you just have to only represent the atoms. And then from there, you would, for each of the bonds, you break them into, split them into the diagonal axis of it. And then the respective, all of the electrons will flow, will just move to its respective place. The lone pairs would stay at the diagonal of the matrix. That forms the bond electron matrix, right? And then with this bond electron matrix formulation, we then right now can actually do mass conservation just based on this representation. So going from the reactants to the intermediates to the product, this is like a nice formulation where we can move from one end to the other, where we just have to compute the delta B matrix to go from A to B, B to C, if that makes sense. Cool. So the sum, I can see the sum of the matrix, which is the electrons, are also equally conserved with at the same time with the atoms too. Right. So with the B matrix formulation, we are then able to actually formulate things end to end, with mass conservation. All right. So we have so right now we have some sort of a learning problem, I guess. So because if we think about the pool of reactants, right? So now we are modeling everything. So this means that there are potentially different types of selectivity, reduced selectivity, stereoselectivity, that would cause different types of reaction that will be formed. So as you can see from this chart, you can see that there are different types of potential intermediates that could be formed. And this means that for a given bond electron matrix, what we're going for is actually a different intermediate bond electron matrix. We're going from the reactants point, we would be doing, so the entire formulation would become a one-to-many formulation, one-to-many mapping. So this mapping in these terms would actually mean that we would want to learn the prediction going from one matrix to the other matrix. So I think in previous literature for image generation, there's like some sort of pixel RN where you would like to generate the matrix or generate the image like one by one. And in this case, like it's also really hard to say to do mass conservation. You would be like, let's say if you do too much once and then your zeros would not follow up, this means like it's still kind of wonky when you do autoregressive of generation of matrix. So I think as we saw this matrix, we see that, oh, this is like a really strong link with image generation, where you can think of, like, let's say if you have some sort of image, because like it starts with a Gaussian, right? And then this Gaussian just moves towards like a picture, and normally the picture does not really change the dimension. So this is actually a perfect use case for diffusion or like flow matching formulation onto this kind of onto this problem. So when we think about the modeling, we can think of, so I mentioned about diffusion and flow matching just now. There's two ways to actually think about this problem. So to reiterate the problem, we now have like one electron matrix, right? So we have the matrices, we have the reactants, we have the intermediates, the product, they all share the same shape. So right now, what you would want to do would be say, you can say, given a condition of a reactant, you want to move some noise towards the delta B matrix. And then that delta B matrix is just basically the arrow pushing that you're trying to learn. Or let's say you could just learn going from the reactants directly to the product. So there's like two ways to think about moving from one matrix to another matrix, right? So if we are going for the first formulation, the first formulation says that, well, we are going from noise to the delta B matrix. So this is actually analogous to how, you go from the noise to this picture of a dot, right? So this assumes a Gaussian uniform distribution, and then you would like sort of stochastically the noise towards the target distribution. Examples of that are like DDPM. There's like score-based models, discrete diffusion models that try to move from specific prior distribution to a target distribution. Cool. So with that, there's a second formulation, right? The second formulation, we thought of the idea of going from a reactant distribution to the product distribution. So this is when it's an arbitrary distribution that you are going from. You are trying to go from some white flower to a purple flower. So this formulation actually builds on top of a arbitrary sampling, arbitrary distribution sampling. So this means that you can either deterministically move over there, or like you can stochastically move there. So there's two dominant ways of thinking about it. Like flow matching, which is the deterministic way, and then the Schrodinger bridges would be like you stochastically move there. Yeah. So this sort of summarizes like what are the dominant approaches in the current generative modeling field. So to actually dive a little deeper into the math, so we would normally see this big equation, or like this equation in diffusion modeling. So it's mainly two equations that actually governs all of these processes. So it's actually one equation, but there's the forward and the backward process. The forward SDE mainly learns the noising process, right? Going from data to noise. And then we have the reverse SDE that tries to actually reverse the noise, or like the noise, the actual picture into like into the image of a dot. So there's the drift term and then diffusion term. So normally when we see this type of diffusion models, we would see the score function, which is normally the learn model, would actually help to do the diffusion process, where you would noise a picture and then you denoise it, and then noise again, you noise, and noise, and then it just constantly push you towards the picture. So this actually captures the idea for the diffusion model, where the drift term, it's normally the drift term over here, is normally kept constant, and then you would gradually noise the picture into an isotropic Gaussian, and then then afterwards you just move the noise back to the image. So this idea is where only these two terms are normally used in the diffusion model. So when you think about flow matching, only the drift term actually matters here. So the drift term here matters is when you would normally learn the vector field of moving from the noise to the picture. So there's no noising. It's just like, because it works on arbitrary distribution, right? It just moves and learns the vector field. It learns the push forward function going from the image, going from the noise to the image. So this is true, like integrating the ODE, helping the image to, helping the noise to actually move towards or generate a probability path that moves towards the final image of a dot. And then, stochastic interpolant would be actually just using both terms. You both use the score function and drift term. This is where you would, so think of it as you would add noise, denoise, and then move towards the target. And then add noise, denoise, and then move towards the target. So it's just, so as you can see, like that equation or these two equations actually just capture the essence of like this three dominant modeling types of generative model. And it's a great sort of way to think about it and reason about it. Actually. Cool. So when we look at diffusion and stochastic interpolant, just to go briefly over, normally approximate the score function by a score function using a model, and then you would have the numerical SDE solver. You would have a numerical SDE solver, which then approximates the dt as delta t, a discrete time change, the dw as the diffusion term, and then it just moves your data towards moves your noise towards your target distribution. And then you can see that for the diffusion term, there's only the s theta that is being trained, but in the stochastic interpolant, both the drift term and the score term is being trained. And then as flow matching, it will be slightly simpler. This is where like you learn the vector field, and then all you have to do is just integrating the learned vector field so that it forms a path towards your target distribution. All right, so at last we sort of we chose flow matching because I think at least for flow matching, as you can see, it's actually relatively simple. And I think the key idea here is that we wanted to sample from arbitrary distribution. This is like very native to how we learn this problem itself, like reacting just the product. And then we are trying to also allow sampling, going from arbitrary distribution to actually to a target distribution that we want. So we initially started off with stochastic interpolant, but it did not quite work well. So I think empirically we love flow matching because of its the ODE solver in itself is relatively quicker than the SDE solver, and at the same time it has a higher empirical performance. Oh, so so over here it's a little dive into the conditional flow matching framework. So the conditional flow matching framework mainly postulates where we are learning the generative model by constructing an ODE. So this is like a vector field that moves towards moves from your prior distribution to your target distribution, and then basically the entire model here. This is the loss function. It's just saying that you are trying to learn the vector field that moves from the prior to the target distribution, and then generally the probability path is not available. So normally we would do some sampling so that the loss becomes a conditional flow matching loss, where the conditional term is just conditioning on the data point. So this is like a nice illustration of what's going on here. So like the prior distribution, this is the target distribution, this is the probability path, and then this is like the vector field, or like, yeah, the vector field that pushes, it's the direction or then speed that pushes you towards the target distribution. So what does it mean in flower?
Sorry, I have a question.
Go ahead.
So did you find that because your like the matrix you have is discrete, does it also apply similarly to how you would do it in an image? Like, do you have a constraint of the numbers should always be integers, for example?
Yes, I think so. I don't have, I actually have it on my previous slide. I actually remove it so that I don't share too much detail. I'm not sure like the audience over here, that's why like I remove a lot of details, but to put it simply for our model, we had a construct where, so you're right that we, it's actually discrete, right? At first that we represent, we're actually learning a continuous value that moves from 1 to 1. But we also have some sort of a rounding step that helps us go from some continuous value back to a discrete value so that RDK can represent the matrix. So we have an extensive output functions. I think it's stated in the paper, and also the code is where like there's something very interesting that we did to conserve conserve the mass, whether in the noise and also in the model prediction and also like let's say the post-processing step after the prediction.
And
Does
so
that
you
make
do that like you do that fix at every step of the interpolation, or you
Yeah.
apply it every
Yes.
time?
So
Okay.
you can think of it as, so for a flow matching paradigm, you would say apply the noise, right? Apply the noise onto the matrix. When you apply the noise, you first do a center of mass of the noise. The sum of the noise would be 0. So when you apply that noise mask, noise matrix onto the reactant matrix, the sum remains the same. Yeah. So there
if
was
I understand, you
Mhm.
make sure that the noise is such that the path you take is chemically relevant, or like that.
Yes.
Everything.
Yes.
Okay.
Yep. Correct.
Thank you.
So yeah, I should have included slides, but yeah, definitely, I can show you more later if we have time. Cool. So with that in mind, we now have a conditional distribution where we start from some prior over here, and then we have some target distribution here. So this conditional distribution is sort of required for the conditional flow matching loss formulation, and then over here we in flower we are treating it as the reactant bond electron matrix to the product bond electron matrix on the one end. And then the conditional probability path is just a linear interpolation that goes from the reactant to the product. And then the vector field is just you just minus it off so that it just remains like a gradient that pushes you towards the target or like the target distribution that you want. Cool. All right. So with that in mind, right now let's summarize like the 3 pillars for flower. So there is the mass conservation that we did, and then there's the arrow pushing where it both tackled through the representation of bond electron matrix. And then for the final problem for the one-to-many mapping, we use flow matching to tackle the problem. So one thing to note that flow matching, because it uses the deterministic ODE solver, we would always get a deterministic sample if we train on the original just the reactant sample. But notice here that we use a noise reactant bond electron matrix where it helps us to create different samples that helps us to learn the one-to-many mappings. So in generative modeling, you would normally just do multiple sampling, so multiple Gaussian noise sampling, so that it helps us to learn the one-to-one mapping at training. But during sampling, you can do one-to-many sampling. Yeah.
One question. So it's one-to-many in the intermediate steps, but the product at the very end is still fixed.
Yes. Yep. Yep.
Cool. Thanks.
Cool. All right. So let's. Okay. So this is a video walkthrough for the flow matching on the bonding electron matrix. So imagine this is some reactants, and then this is the matrix representation. Over here, you would now project it into a 3D form, and then you would add noise. So just as I mentioned, and then you would slowly, gradually do flow matching on it, and moves you towards the product bond electron matrix. And that final product bond electron matrix would then be this product. So this entire process is the sampling process going from reactant bond electron matrix to the product bond electron matrix. Cool. All right. So with that, let's talk a little about the architecture. So the architecture here is that, let's say, given some intermediate steps that we have here, we would first project it into the bond electron matrix and atom identity, and then feed it through some noise, and then use radial basis function, because all of these are scalar values to make it into vectors. And then atom identity also projected using a one-hot encoding, and then timestamp embedding would be used. There will be a sinusoidal encoder that encodes the time, and then that feeds into the transformer block that helps you to predict lone pair prediction and also the bond prediction. So that constitutes to the delta BE matrix, and this delta BE matrix is is the structure transformation that is being applied to the current intermediate, and then scaled with time, and then that forms the next product. Yeah.
One question. I don't know for flow matching, but for diffusion, you set up the number of steps that you take. Is it the same for flow matching?
Okay, so for diffusion, you do number of steps, right? So that is because like the time scales from 0 to t. The t is like can be any arbitrary number, but for flow matching, it's like 0 to 1. So you would like discretize your step into like 0.2, 0.4, 0.6, 0.8, like that until it reaches 1.
Okay, so in that case, say that you have 0.2 time steps, so you have 5 each, right? 5 intermediate.
5 each.
But what if your reaction has only, say, 2 elementary steps between reactants and products?
Oh, okay. I think this is a common misconception. So think of it as currently what we are focusing on in this prediction is actually just going from it's just one elementary step. So this entire flow matching just flows from one elementary step. And then for the next step, there's also, if you pay attention to the one of the code that we wrote, is that we have a beam search. So this you can think of the function call is actually the function call from one product to an intermediate is a flow matching, and then moving on to the next one is a next call of flow matching. So it's not like 0 to 1, then it gets to product. It's like 0 to 1, it gets to intermediate 1. Yeah, if that makes sense.
Yeah.
Okay.
Super clear.
Yeah. All right. Cool. So with that, let's move on to the sampling. So this is where this actually demonstrates it relatively easy. So this is like some reactants, and then you go to the intermediate. So this is entire 0 to 1, and then it gets you to the final product. No, not the final product, the intermediate. And then this intermediate would then do another step sampling, and then this sampling will get you to the product. So you can think of, like, let's say if you have a one-to-many mapping, this can form another intermediate, and this intermediate can form another, let's say, intermediate, and then before it goes to another product. Yeah. So like there's like a branching tree that like grows out from the initial reactant. Oh, all right. So with that in mind, all right. So let's talk a little about the performance of the model. So going from the mass conservation, this is where we see that most of Flower's prediction are atom, not most, it's like almost, most of Flower's prediction are valid smiles, that or at least the atoms and the protons and also the electrons are all conserved. But at least for molecule transformer and graph to smiles prediction, most of their smiles and predictions are not mass conserved. So it's like easily evident from this chart over here. All right, so for the top tier accuracy over here, we sort of demonstrated that Flower has matches or like outperforms a little bit as compared to graph to smiles in terms of that prediction. And this is so mainly why we do have this Flower and Flower large here is that when we notice that this Flower model here is a relatively small model. If you can see in the in our paper, is that we use like a 2 times smaller or 3 times smaller Flower model, and like that sort of like matches the performance. And then if we do Flower large, which is actually not larger than graph to smiles, if the parameter counts is still like way a little lower than graph to smiles, we're able to in some way outperform or like just at least matches or outperform a little bit of the best model currently that we are comparing against. Cool. And then I think this is the really exciting part, where this was one of the times where the idea for inductive biases actually helps with your prediction in low data regime. This is where the I'm not sure if maybe if you guys are familiar with the equivariance type of argument, is that you don't really need equivariance, you just need more data. So this one is just to show that we see that because reaction data is like very limited, so we actually by injecting those inductive biases on top of this model, we're able to see that even with very low data, especially for the step accuracy, Flower is able to actually start recovering or actually predict reactions accordingly. So this is just by training on 500 and then predicting on 220K test set. So we are able to see a very high step accuracy recovery due to the inductive biases. The law of the conservation and the representation itself actually changes this, or actually it helps to perform this well. Yeah. All right. So this goes back to also how Flower captures reaction condition. So in this case, we see there are different catalysts that are involved in this reaction, where we can see there will be actually different types of product that will be different types of product that will be formed by actually putting different types of catalysts. And I think this is one of the key points that we're going for, is that for a lot of the end-to-end prediction models, there's no byproducts, right? But right now, if we enumerate all the steps, we basically get the training data for byproducts, and that helps us to sort of like formulate and helps us to develop models that are able to be trained on different types of byproducts corresponding to different types of catalysts that is being input. Right. And that moves us to the reaction conditions. So this is also a reflection of the training data. This is where we see that with different bases that are being used in the model, or in the model, it actually reacts to forming a different reaction, or it actually proceeds to a different reaction. So over here, there's different types of bases, helps us to get to different products, and that kind of implicitly shows that Flower captures based on the data statistics, actually knows when to predict a reaction, when to not predict a reaction, corresponding to the pKa. So another thing that was pretty exciting for our work is that for unseen reaction causes, so this is when the reaction cause is not really seen in the data set, how did Flower and the other sequence-based models perform? So for the sequence-based models, as you can see, due to very heavy alchemy prediction, they either stop in the first top one pathway, and then, or maybe let's say they go through the top two pathway, but they did not reach the product, or they would start actually doing alchemy and then creating reactants or intermediates that they are not desired. So this is when, when you look at for chemists to look at it, it's like, oh, okay, do I really trust the prediction if it's like inventing atoms here and there? So this is why we try to ground our models back to the mass to obey some mass conservation, so that in some way, even though the prediction sometimes may not make the most chemical sense, but at least one of the few key principles are being conserved. So by conserving the key principles, Flower is actually able to predict the plausible pathways for the major and minor products. So as you can see, there are like a lot of steps. So this means that Flower has to every step is like multiple model calls that actually refines to this step and refines to this step to this step to this step. That is probably 10 steps. And then this helps us, as we branch out, we are able to form both the major product and the minor product. And what's more actually interesting is that this overall reaction actually, the major product and the minor product actually corresponds, or the intermediates actually corresponds to the DF, to what is kinetically favorable, or kinetically favorable, thermodynamically favorable, is where we see this type of the blue pathway, which is the major product, actually was the lower energy pathway. This means that Flower, in some way, by learning on the intermediates, we are able to predict intermediates which correspond to the least the most favorable pathway for the major product. Yeah. So
one question there. Is the data that you used to train that you pointed to the other paper that I haven't read? That's why I'm asking. Is the data that data also coming from like this DFT like optimized pathway?
It's not really, because as we or more like, so if the textbook literature in the textbook literature pathways or elementary pathways in some way have the biases towards intermediates which are energetically favored, then maybe they sort of capture it. It's almost implicit, because like when you write out elementary steps, there are some elementary steps through transition state sampling, that that is the most probable one, but right now it's just based on textbook. So if the textbook has that, then it has that. If it doesn't, then it's more like it is an inferred or maybe an emergent property from flower that predicts this type of pathways. All right, so
there's another in the chat, which is how do you deal with different numbers of atoms in your input molecule and output molecule? Like I assume it's if you have an N2 and then you have an N, like two N's that are separate.
Oh, so like you're saying like nitrogen in one atom, like let's say in one. If we go back to the slide, it will be probably like nitrogen in one atom, like in one fragment, and then nitrogen in another fragment. They are both nitrogens, right? Is that what the question actually means?
No, I know. I assume the question is more Daniel. You can maybe frame it better, but yeah. Easier.
Yeah, I was curious if you have more atoms in the input and output. Do you need to change? Do you need to pad the matrices?
So more atoms because this entire idea is building on top of, like, if you start from some reactants, then your product or like the entire product pool will share the same number of atoms. So we would not be creating or destroying atoms, right? In previous predictions, you just predict the major product. So definitely there's a reduce in the number of atoms being predicted. But right now we're assuming that you don't invent, and you don't invent atoms out of vacuum. You don't delete them out of vacuum. You keep everything from the start to the end. So that's why like there's no more or less. Like it's the size of the initial prediction and the output prediction will be the same. That makes sense?
Gotcha. So do you retrain on different reactions?
Basically you would. So we will sort of cover the retrain part later. We call it the fine tuning part, but I think in general it's just you would just train it on a lot of elementary steps pair, where like elementary steps pair, product intermediates, reactants intermediate, reactant intermediates product, and then you just train on a lot of pairs, and then the model would gradually capture the statistical way of moving the electrons based on the training data distribution. Does that make sense?
Gotcha. Yeah. Okay. Makes sense. So there's it's always the same input and output for one model.
It's always the same input and output.
If you change the input and output.
Basically, you have a large model. You basically have one model that trains on all of the elementary steps. If that makes sense. And then all of the elementary steps, the A to B, A and B are sort of the same size.
Gotcha. Thank you.
Cool. Right. Okay, moving on. So this is a flower and generalization. So before fine tuning, a lot of like the non-unseen reaction classes over here, with some overlap of elementary steps in the training set model. The model is able to start predicting and generalizing to these cases. And after fine tuning, we are able to see even larger bump towards all of the wait, let me see. Is this how we should be reading it? Oh yeah. So yep. So this is before fine tuning, and then this is after fine tuning. So before fine tuning, there's some generalization that that is already happening because all of these are unseen reaction classes, and then we're seeing we are already seeing generalization, and then after fine tuning just on 32 examples, we are able to see the that the model actually learns a lot of this cases already. So as we can see over in the normal fine tuning, a lot of the models out there, they fine tune on 2,000, 25,000, 9,000 reactions. But I think for Flower, it's very non-data hungry. It's very data efficient, where it just picks onto like 32 examples of reaction, and it's able to start generalizing to a lot of this unseen reaction classes. So, yeah, go ahead.
One question, maybe like going back to the previous question is, when you see different reactions, they will contain different number of atoms. So do you like paths, or what do you do in that transformer training?
Oh, okay. I see where you're going. Yes. So let's say in a batch, right? In a batch where there are some reactants where it's five, and then 5 atoms, let's say, then another 10 atoms, like you would pad it. Like if you want to train it in a batch, then you would pad it. And then, but in general, like the transformer would just take in the max number of atoms needed and then just learn it through. Yeah. But definitely, yeah, the padding is still needed because the training, there are still different sizes, and then you still need to train it. Oh, like that.
Sorry, the output size then is also based on the max output you see in all of the data?
The max output, yes. So let's say the max output, you would still pad it, right? Let's say you train one which is 5 times 5, another one is 10 times 10. You would have in the 5 times 5 all those padded regions, and then those are not included in the loss, right? And then you have the ones in between, the ones in 5 times 5. You do that on the loss. So when it's trained, then it's not really affected. Yeah. In some sort, the padding is still needed, like during training, so that we can handle different lengths of data. Yeah. Cool. With that in mind, so this is fine tuning, and then more on the reactions, and then the reaction part. I think most of them are able to generalize well. I think for transamidation, we had this one caveat where because of there was one elementary step that was overly represented in the training set, and then because it was too biased to actually forming that kind of bond, so fine tuning on it, like it was sort of like have to move it further, like to tell it, oh, there's another possibility for forming a different type of bond. Yeah. All right. So with that, so one question that someone might ask would be, after fine tuning, do you actually forget a lot on like what you actually learned? So the answer is actually no. Flower actually still are able to perform really relatively well, but I think for for most of the reaction class that is being trained, but I think there are still more handling required or needed for the cases where we know that, let's say, some elementary step is pretty biased in the data set. How do we sort of de-bias it? So so this is one of the cases where if the model are trained on this one exact sample for a lot of cases, let's say you just input the different case here, like forming a different bond, then in some way, like it would now require more time to get used to it, like in this case. Yeah. All right, cool. So in conclusion, right now for Flower, mainly it's able to conserve mass and electrons, as contrast to previous model, and all of the electron movements move all at once. It's the first work that applies flow matching for reaction outcome prediction, and then we sort of reformulate it in terms of electron redistribution, and then it matches conventional models like SMILES in terms of like Tokyo accuracy, I actually chose matches instead of outperforms because it's just like a little bit, so don't want to overclaim things. And then it's able to help with fine tuning on minimal reactions as compared to existing works, and it mainly captures the chemical intuitions based on the training data set that's being trained. So with that in mind, I'd like to acknowledge like the people back at MIT, namely all of the authors that I work with, and I think I'm happy to take questions. Yeah.
Awesome. Thank you so much.
Thank
There's
you.
one question from QA. They ask if you can share the slides. Maybe you can give your email and they can contact you later.
Oh yeah, definitely. How do I? Let me see. Where is?
Just in the chat, you can your email, or I can send the email later.
Oh, you can. Oh yeah. I'll just put my
Okay.
my personal email here.
I have one question.
Yeah, go ahead.
So you mentioned that you're doing right now flow matching on continuous values. Is there a reason why you didn't do discrete flow matching?
Oh yeah, this was like I think just to kind of this was like we actually initially started off with like we wanted to do discrete values, like it sounds more intuitive, but apparently after discussing with my PI, he's like, oh, in the continuous case, you're able to sort of zero sum out your prediction. So the delta B matrix sums to zero, right? Ultimately, when you change all of the change electrons, you cannot invent new electrons. Like the change should be zero. No, the sum of changes should be zero. The sum of changes should be zero. So with that, we just thought that continuous values, like it's an easy way to just sum things and then like just call it a day. But for like discrete, it's like you have to like change discretely but not violate the principle. It becomes like it's hard to do, but it's definitely an interesting direction to pursue. Like because like, natively it will be more interesting to represent it that way. But it's just I think in terms of architecture convenience, we just like zero sum will be a very very convenient way to do it. So that's why like we stick to the continuous representation.
Okay, and you enforce this rule with the rounding algorithm that you mentioned before.
Yeah, with the rounding algorithm. Yeah.
Got it.
Cool.
Are there any other questions in the audience? Okay, I guess not. So we can close it here. And we're actually on time too.
Yep.
Thank you so much. It was super interesting. Actually, I have one question.
Yeah.
Do you have a follow-up? Are you working on a follow-up on this? Or
not really. Right now, the lab has changed a lot. I think a lot of the people here in this image actually they kind of left. But there's one guy, you can definitely email Connor. I think he will probably reply. But there's definitely someone that is taking up what's next for Flower. Yeah. But I'm not sure exactly what they're doing. But it's just because I've already left the place, so that's why definitely if you want collaborations or you have ideas to work with them, like definitely talk to them. Yeah. But as for now, I'm not exactly sure what's the direction that they're trying. But definitely they're pushing something new. Yeah, for this. But I think one of them is just at least increasing the number of reactions. Like we are covering just this much, and then we're trying to increase to more enzymatic reaction, different type of reactions and stuff. Yeah.
okay, really cool work. Again, thank you so much for presenting.
Oh, thank you so much for having me.
Have a nice day. See you.
Bye. Have a nice day.